Okay, welcome everyone to my continuation of what is category theory. Today I would like to talk about duality in categories. Or, while strictly speaking, there will be something, well, it's called rigid and pivotal categories. The motivation is as follows, at least for me. So this lecture series, or whatever you want to call it, video lectures on category theory is nearing its end. And what I find personally very nice about category theory, it's of course a matter of taste, absolutely a matter of taste, are string diagrams. So I love string diagrams. It's kind of this diagrammatic way of thinking about abstract concepts. And of course, you can, if you think about abstract concepts, you can kind of paste into your kind of function if you want. The function of string diagrams, kind of your favorite problem, and you can try to express your favorite problem in terms of diagrammatics as well, which is really a cool and nice idea. Yeah, but kind of a little bit disappointing. Up to this point, string diagrams are not as powerful as they're supposed to be. So there's some kind of flaws in the setup. So right now, string diagrams for Monoidal categories kind of want to be a two-dimensional calculus, but somehow something is missing. Right? So you have a two-dimensional calculus, you draw two-dimensional diagrams, but you are not allowed to do, so you draw them on the plane, so on your piece of paper, but you're not allowed to do all operations that you would like to do on a piece of paper. And that's really not very satisfying. That's very disappointing, right? You just try to, I should do this isotopy now. That's how it looks like, but I'm not allowed to because my calculus is not rich enough. And the whole point is now today and in the next video to address how we can, well, improve the calculus if you want. And this is how it works. And it's kind of generalizing well-known concepts from vector spaces. Of course, vector spaces is kind of the favorite example, at least in this series of videos. Okay. So here what I want to do is I want to enrich the string calculus. And what I would like to do is, well, I have string calculus, and the only thing I do, remember, string calculus just means I have an object and a morphism on this object, in this case, identity. Morphisms themselves would be just coupons, but here's the identity on this object, and I want to enrich it by putting an orientation on my diagram. So now I have an oriented calculus, and I can kind of distinguish between an object and its dual, the dual object. I give it a little symbol up here by looking at the orientation. So my convention here, just my convention, would be I put an orientation. Whenever it's upwards pointing, that should correspond to the object itself. And whenever it's downwards pointing, it actually should correspond to, let me get rid of those symbols here now, because I have a downwards pointing, this actually should correspond to the dual object, whatever that means right now. So right now, I just go with it, right? I kind of want to have dual objects in my category that I would like to encode by an orientation. And yeah, dual object will be something like a dual vector space, just more general. And what makes this object dual is that there are certain maps, and there are 4 versions of this map, right? So you have an orientation now. What you should try to do is you should try to do a cup or a cap in all possible ways of orientation. And the cup and the cap, if you stack them together in, let's say in this way, you have this cup morphism and identity, you have this cap morphism and identity, you get this snake type thing, the zigzag, and you would like to straighten it out. Right? So that's what I want my category to satisfy. I want my category to satisfy that we have duals, and they are duals in the sense that, well, you have evaluation, co-evaluation maps, and you can straighten out diagrams. So this is my string diagram wish list for dual objects. That's what I want to do. Right now, we don't have any example. That's just what I want to do. And of course, I wouldn't tell you the story if there wouldn't be any examples. Stay tuned. But what I would like to do is now I would like to enrich my calculus such that it gets much more kind of like a planar calculus. And it will be built, and that's kind of very surprising, and you can really rigorously prove that. Of course, I won't do that in a YouTube video, which is only something like 10 minutes in length, but you can really rigorously prove that your whole calculus will be topological in nature. So what you can do now in this calculus, for example, you can define a dual morphism. I just talked about a dual object, but you can define a dual morphism. Remember, a morphism is just a coupon, and I add this little stake here, and I call it a dual morphism. Right? So this goes from X to Y, and it just turns around. This is a dual morphism, and there will be some compatibility conditions. So there's another dual morphism. Let's not worry about that too much. But basically, you take your morphism, it is something like this, and the dual morphism, you just use your maps, you turn it around, and you think of it like, well, this is just by the definition. But of course, you think of it as just straightening it out, it turns on its head, and you have the dual morphism. It's kind of a nice way of thinking about dual morphism. It's just your morphism turned on its head. And then you go on, kind of have the correct calculus built such that you have the natural relations among diagrams. You can slide morphisms across cups and caps. And, well, remember that I would like to think of this as this kind of on its head. And of course, if you slide it across a cup, it is kind of on its head. I can't turn my head, I'm very sorry. But so it's on its head and it looks the other way around, and you get the natural sliding rules, and you can really prove a lot of cool things. So this is a diagrammatic proof, which I'm not assuming you understand right now what it's actually proving, but the proof is pretty simple. I kind of want to prove that the GF morphism here on this cup is the same as the FG morphism. And what I do is I just slide everything around. So I take F, slide it around, it turns on its head, and then I slide it around again, it turns on its head, and now it's on the top, and kind of I've proven this trace type property of GF equals FG in this case. And it's really nice. So what we want here is, so build kind of a diagram calculus modeled on something. I will tell you in a second what it's modeled on, such that you have dual objects, dual arrays, dual everything, and dual is kind of turning pictures around. It's kind of the dual rule, and it's kind of the dual rule if you want, the rule for duals. And this gives you a topological calculus. This is really what we wanted, right? Now, your string diagrams should get a really completely topological flavor. You have some little boxes somewhere, you can shift them around. Just be careful that they might turn on their head. Otherwise, you just pull them around like you want. And this looks very nice and looks like a really, really good way to have string diagrams around in a category. We can't assume that it holds in general. So what I'm saying is I'm looking at a category having this extra structure, and then I get a nice diagram calculus, right? So kind of enrich your original diagram calculus. And where does it come from? Well, there's one category that we by now all hopefully like. Of course, my good old friend, vector spaces again. And in vector spaces, well, strictly speaking, finite dimensional vector spaces, I will elaborate that on a second. Of course, everything has a dual object. Maybe I shouldn't say of course, but there's a dual vector space, which is a dual object. And the co-evaluation maps are the usual ones. So maybe the evaluation is a little bit easier to think about. It's just, well, what is a dual vector space? A dual vector space is linear forms, and you can just take your pair here of a vector in the linear form, and you just evaluate the vector on a linear form. And there's a corresponding co-evaluation map as well. It's just really the dual map, but maybe it's a little bit harder to think about. So in vector spaces, we have all of these maps, and you can check that they satisfy the zigzag relation. And that's what we want to model it on. So actually, we have an example where the diagram calculus I showed you before works. It would be vector spaces, to be completely precise, finite dimensional vector spaces. So fun fact as an aside here, the dual of a vector space is isomorphic to the vector space itself if and only if the vector space you started with is finite dimensional. So in infinite dimensional vector space, it just doesn't work. And this will turn out to be that this map is not invertible in a nice sense. So you really need a finite dimensional here, which is not a big deal, but because, well, who cares? I mean, infinite dimensional vector space are a little bit scary anyway. You probably can't really attack them using methods of algebra anymore, or let's say methods of pure algebra, but you may probably need some functional analysis or something, which is not unexpected. So let's just ignore that we are not talking about all vector spaces. Finite dimensional vector spaces are good enough anyway. So I repeat it, a vector space has a nice dual in the sense that it's isomorphic to the original one, if and only if the vector space is finite dimensional, and this is what I'm using here. Anyway, so that was just a waffle as an aside, kind of a side project if you want. The point here is the vector spaces satisfies our wish list that we had before. So we actually get a nice calculus for vector spaces. And this is kind of the motivation to define those pivotal categories. That's what they're called. So an object in the monoidal category has a dual. So that's what you need to do before. And of course, I denoted by the same symbol as before. If you have those, well, cups and cap maps in the corresponding four orientations, satisfying the zigzag relation in all possible orientations you have around. And this is what people call a pivotal category. So this is an extra structure on your category, the structure of having duals in appropriate sense. Right? So and duals are actually pretty nice. So duals are like universal objects in your category. So they might not exist. Example, it would be infinite dimensional vector space. Infinite dimensional vector spaces do not have duals in this sense. They have a dual vector space, but it's not a dual in this sense. So they might not exist. But if they exist, they're unique up to the usual unique isomorphism. So we could talk about the dual. Okay, and I don't want to go into details what a rigid category is, but you can kind of make a weaker notion. Distinguishing basically the orientations. Distinguishing basically whether you have a left or a right. Doesn't really matter. Well, it actually doesn't matter for certain examples, but for today, it doesn't really matter. And kind of a really nice fact here, it's a really beautiful. So you cook up this notion of duals based on this example of a dual vector space. But actually then, whole point of category theory, right? It gets more general. And a good example of a category that has duals is end of C, which is rigid in the sense, well, that you need to distinguish left and right. And the left and the right dual are actually the left and the right adjoint functors. So NC is the functor category, right? The objects are functors. So duals would be functors. And the duals in this case are the left and the right adjoint. Remember that we had this, well, or maybe you don't remember, but anyway, for adjoints, you have exactly this zigzag condition for them to exist. So adjoints have the zigzag condition built in, which is pretty cool. You just need to be careful here with left and right because you know they're different left and right adjoints. But anyway, this is a cool example, right? Two examples. One of them vector spaces, and the other one looks very different endofunctors on categories. That's kind of pretty cool way of thinking about duals, I think. Adjoint functors are duals in that sense. Yeah, and let me just finish by showing you kind of the power of this calculus. So the calculus is really powerful. So here's a statement about pivotal categories formulated in kind of a topological way. So two diagrams are equivalent, even only if they're related by scaling. Sure, scaling is something we like because it's no problem, or by planar isotopy. So now we really have a planar calculus, right? They're related by planar isotopies. You can really pull your strings around. It's really, really powerful. It's really, really good. Instead of doing some algebraic calculation, you could really use your topological intuition in those categories. So just pull strings around. Just be careful if you cross them. You need to turn your head and you get duals and everything. It's really, really, really nice, right? So it works as soon as you have some nice pivotal calculus. And this is really a planar calculus and the whole point. Just one warning here, it's really planar. So if you draw a diagram like this, and that's the certain diagram you might like to draw, it's not the same as pulling the H outside, right? You just can't pull the H outside here. And I'm thinking here in this notation about H as kind of a diagram from the monoidal unit to the monoidal unit. Because the whole point here, I haven't said this clearly enough, is we already have an underlying monoidal category to make this work. And I just don't like to draw trivial things, so I don't draw them. So H is just a floating bubble, a morphism from the trivial to the trivial, and you can't pull it out, right? It's planar calculus. That's the whole point. Okay. Duals in categories is slightly different than duality for categories and so on. So duals in categories depends a bit on your viewpoint. Either modeling vector spaces, dual vector spaces for finite dimensional vector spaces, or adjoint functors in kind of a more categorical framework, like in the definition point, like if there's a dual, and if there's a zigzag type relation for that dual, you call it a pivotal or rigid category, depends a bit what you want. And the point is the calculus then gets really nice, beautiful, two-dimensional, planar isotopy is absolutely great. and we are actually there where we wanted to go, which is pretty cool. So, right, I say it again, you now have planar calculus associated to certain types of categories. Doesn't work for all categories, but for certain types, like vector space type categories. Anyway, I hope you like string diagrams. I hope you enjoyed the video, and I also hope to see you next time.